is there any other questions, or I'm just going to start with Pack 10C? Oh, okay, so I'm going to talk to you now more about the analysis of network topology. We're going to focus on models for generating networks. And we're going to first talk about two different things, what's called ER models and small world networks. So first, the ER model. This is probably the original network model. It was developed by this very famous mathematician named Erdos. Maybe you've heard of this term, the Erdos number, and this is related to his network studies. That's how many links you are away from this famous mathematician in co-publication. And he developed this model, which we're going to talk about. And then we're going to talk about two other models, the Watt-Strogatz model and then the Barabasi-Albert model. Both of these models come from right around 2000. So the ER model is pretty simple, but it's sort of the background that we use to talk about these things. So here we imagine we start with a bunch of vertices which don't have edges, and then we connect a pair of vertices with a certain probability. And the probability, it's called P sub ER, we can vary it. And then one of the things that he noticed is that as you vary that probability, the sort of properties of the graph kind of appear very suddenly at a particular value of PAR, which is around 1 over the size of the number of nodes. And under that, there's really just isolated bits, and then a graph starts to emerge. Now, we'll come back to that probability for PER. That's a sort of random network. But I think the way to think about this is to compare it with other models. So let's talk about a Watt-Strogatz model. And this is a very, very similar model. So in this model, what you imagine is you sort of take the ER graph, which is essentially a random network, and you have on the other extreme a kind of completely regular lattice-like network. So now if we start with the lattice-like network and now we rewire it, we grab an edge with a particular probability and connect it to another vertex, okay? And then we keep doing this with a given probability. Obviously, if the probability is pretty large, we're going to essentially end up with the random ER-like graph. And if it's very small, we're going to have a very regular lattice. But what Watts and Strogatz observed around 2000 was that in the middle, you have this kind of interesting graph, which is you might call it a small world network. And to think about what this small world network thinks, it's useful to think about some properties of a regular lattice first. So regular lattice, all the neighbors in a regular lattice are connected very well, but there's very little long-range connectivity. And so that what we'd say using the terminology from last class is we'd say we have a high clustering coefficient, but there's a long path length. Whereas in a random network, the clustering coefficient is not nearly so high, but things are actually pretty globally well connected, and you have a low characteristic path length. And one of the interesting things that Watts and Strogatz observed is that for intermediate values of this rewiring thing, you preserve your clustering coefficient, so the network remains clustered, but suddenly you start to create these short paths through the network, and that's why the network is described as a small world network. And this is actually thought to sort of represent a little bit of what we sort of see in the world, where there's little communities, but then they're randomly connected together, and that leads to overall fairly small path lengths in the whole network. And when they talked about this, they looked at some of these famous examples of networks, the network of film actors, the power grid network, nervous network, and so forth. And they looked at the clustering coefficient and the shortest path in the network. So the small world network is this essentially a thing that has a relatively large clustering coefficient and a relatively small characteristic path. So those are sort of two things. And I'm going to talk about a third type of network, and this is the Barabasi-Albert model, or a scale-free network. Now, the ER network or the Watt-Strogatz model, they have a characteristic scale. So if you think about that probability of in the ER diagram, if you think about how many connections things are going to have, it's going to be kind of sort of distributed around that sort of central value. So the PER kind of talks about the average degree of the amount of connections you're going to have. And then, you can have some nodes that have more and some that are less, but it's going to be kind of distributed around that. And that value is a kind of characteristic scale for the network. So on average, you have this amount of connectivity. And the Watt-Strogatz model has a similar type of scale, and the scale is the kind of characteristic degree or connectivity that you have. And Barabasi and Albert looked at a somewhat different type of network in around 2000. They looked at what's called a scale-free network. And here, the degree distribution, that is the number of nodes with a particular degree k, that doesn't have any characteristic peak. It just sort of falls off. And if you plot it on a log scale here, that fall off is a straight line. And this type of thing is often, people use the term a power law model. And so the degree, is related to the sort of in relation to this formula. It falls off with the sort of degree to the minus gamma power. And they found that, many commonsensical networks had this property. The World Wide Web, these power grids and so forth, had this scale-free property. And the key idea here is there's no peak at a particular degree. That just kind of falls off. So there's no particular scale that you could immediately see fits this network. And here's, this is a picture from Scientific American that kind of illustrates this. Again, here's a sort of random ER graph network, and which is a typical node. And here's the power law one, where there's no more of a sense of a typical node. It just kind of falls off. And one of the nice comparisons people have for this is kind of the road network, which is to some degree a random network in the United States. It's just connectivity of different cities. But there's a kind of typical connectivity that you tend to have. And then there's what's called the airlines network. And the airlines network, as we'll talk about, grew in a very different way than the road network. I mean, there's some cities that really have a disproportionate amount of flights going from them. They're hubs, and we'll talk about this in a second. And this leads to this power law type of behavior, and it looks a little bit different. Now, so one of the ways of getting a sense of the scale-free network is to think about kind of a growth model for networks. So in the ER graph, we just kind of connected up things with a given probability, and that was fairly uniform. Now in the Barabasi-Albert model, we're going to introduce this notion of preferential attachment. And so what we're going to have is we're going to have a number of vertices, and then at each kind of time step, we're going to add to them. But the probability that we add is going to be proportional to the degree of the vertex. And so what this means is this is essentially the rich get richer type of thing. So you're going to add, the probability of adding is going to be in proportion to how many connections you already have. So if just luckily a certain node gets a few connections, it's going to keep getting more connections too, because you're going to preferentially add to that node. And here's a picture from Scientific American that kind of shows this network growing. You're starting with 2, and then you add something, and notice how you're adding on more and more to this central node, which is becoming a bit of a hub and so forth. And preferentially, not exclusively, not all the time, but preferentially you're adding onto that network. And then there's a sort of way that sort of naturally you can see how this type of thing fits with a sort of gene duplication model. So if you imagine you have two proteins that they're interacting, okay, but imagine that they are duplicated. When you duplicate one node, it will tend to, or one protein, it will tend to go back and interact with its original partners. So that's a kind of type of preferential attachment. And you can sort of see a hub network that has a lot of nodes. If you tend to just uniformly duplicate, it's more likely you'll duplicate on one of the things that already has a lot of connections that will then tend to interact back with that central node, and that node will kind of get, how should I say, more connections, rich get richer in a sense. And so this preferential attachment mode, it actually fits very well with a biological context, where in relation to gene duplication provides a very simple way to see how such a thing, that type of network might grow. And that might explain why people had observed that the protein interaction network has this scale-free